All right, so I got time for a really short one today. By that I mean like a good half an hour. um, but I do want to just give a quick, moral high horse lecture. If you only got 10, 15 minutes, half an hour is great. That little bit of everyday work adds up, and before you know it, you have accomplished something really significant. So, I'm just going to take the limited time I have this morning and contribute to this ongoing thing I've been doing, reading this book, and before I know it, I'll be done reading it completely. So, there is a primary factor that influences this outcome. The outcome, because remember, uh, in the last video, we learned about underfitting, we learned about overfitting, and we learned about dark knowledge, as it's called in this context, which is a somewhat, you know, widely used term in the industry, but you really won't hear that term in other parts of the industry. I actually used ChatGPT in what I thought was a pretty clever way to kind of explore other areas of the, of this field. So we can see we've got academic researchers, industry professionals, open source contributors. These are all different sorts of people, sorts of roles you would see that might use this term dark knowledge, and each of them is assigned a probability that they would use it. Educators, content creators are very likely to use it. Hobbyists and enthusiasts that just learn from the content creators, the educators, very likely to use it. But the actual ethicists and policymakers whose goal is to work with the government and create some laws or regulations really aren't likely to use these kinds of terms. Um, in addition, open source contributors who are really down in the weeds and developing real products aren't likely to use it. And then the third least likely to use it are the academic researchers. And these are kind of the groups I want to be the most involved with, especially the open source contributors. Um, and I would say the ethicists as well. That just kind of interests me. So I thought this was a clever use because I didn't know any of this before I talked to ChatGPT. It might not be accurate, but it's a useful aid to my thinking about this subject matter. So there is a primary factor that influences the outcome as to whether your model is useful or not. The complexity of the model. The complexity of the model is defined not in absolute terms, but in relative terms to the dataset's type, complexity, and volume. This may be a bit confusing because how do we measure complexity? Is there a complexity score we can use? No, there is none we cannot measure, but it is something we need to play with by using different algorithms or size models, which may expose a larger or lower complexity. For certain types of models, such as a neural network, the complexity is directly related to the model's size, how many layers, how many nodes per layer, etc. However, how to compare the complexity between one type of algorithm and another one is not obvious or even possible at all. But the reality is that the complexity of the model drives the results above that we saw with overfitting, underfitting, or having a useful model. Number one, if the model is too simple, it usually means the number of parameters in it is small. It may not have the ability or degrees of freedom necessary to learn the different internal parameters of the data. So no matter how many iterations we use on the training data, the result will not be good. It is simply too simple. It will not work well neither with the training data nor with the testing nor unseen data. We will need to choose a more powerful model to improve our results. If the model is too complex, we are on the other extreme. The model has a large degree of freedom to learn to capture behaviors, and while we would like the model to learn the common patterns in the data, it may end up learning also spurious behaviors, which may simply be the noise that every metric has, even perhaps from the data capture process itself. It is too complex, too powerful, and ends up learning things it is not supposed to. In fact, we could argue that it is not learning, it is memorizing. The consequence is that it will produce surprisingly good values, very low error, for our training dataset, but when presented with new, unseen data, it will not generalize well because it has learnt patterns which we did not want it to. We will need to decrease the complexity of the model in relationship with the data. So either we make the model simpler or we evaluate if the problem is that the data is not properly representative of reality and we need more complex data. Let me get back to this point later. And the point to get back to is this idea of overfitting, that it basically just memorizes the training data. But moving on to point number 3. If the model is the right one, then we will get good results both in the training data and the testing or validation data. That means the model has been able to capture the key internal patterns in it and ignore the noise or spurious patterns, which may also be present in new and unseen data, but will likely be different. The error will be a function of 2 factors at the output, the bias and the variance. When there is high bias in the model, it means it is systematically deviated, driven by its low complexity. When the model is very complex, it will result in a lot of high variability in the result. It will not have a high bias, but a high variance, ultimately contributing to the total error. There is, therefore, some optimal point of complexity where the model is accurate enough, low bias. However, it does not learn noise and spurious patterns, which would contribute to high output variance. A clear sign of overfitting is when the model delivers surprisingly good results in the training data, but the validation error with the testing data set offers poor results. The goal is to find that optimal middle point of complexity where we achieve a good enough result for both. You might always find ways to improve your training error, but most of the time it will be at the expense of having a worse generalization, which is not a good outcome. Alright, so let's see what ChatGPT has to say about this graphic. Alright, so the voice isn't working. I'm not sure what's happening with the playback. I can't hear it and it's not registering in OBS. I guess I might want to take a quick break here. I'm not sure why it's not reading it back. It's also taking a lot longer to print out than it usually does. All right, so I don't know why. Anyway, so yep, it's two graphs. Left graph illustrates how total error, bias, and variance change with increasing complexity. So with increasing complexity, we can see bias goes down, variance goes up, and total error goes up, which is the counterintuitive thing, because you would think the more you train it, the more complex you make it, the better it is. But no, because then you fall into that overfitting problem, that memorization problem, where now it can only recognize your data set, and it can't take away insights from that data set. It can only just exactly match that data set. So we can see we've got this dotted line here that shows kind of the ideal place to stop. You want that error rate to be as low as possible, and we can see it starts increasing the more complex the model gets. But it decreases the more complex it gets to a point. So you need to find this minimum error point for a model, and then same thing with and then with bias and variance, you want those to be low as well. But bias you don't want to be as low as possible, because that would lead to overfitting. Variance, there's a point where you don't want that to be as low as possible as well, because variance is the different kinds of answers you can get. So if you can't get any different kinds of answers, then that's a problem. If you get too many different kinds of answers, then that's a problem as well. I think I might be wrong about what variance means there. But yep, so the total error is a combination of bias and variance. The bias decreases as complexity increases. Bias is the error introduced by approximating a real-world problem, which may be too simplistic. Variance increases with model complexity. Variance is a measure of how much the model estimates would differ if different subsets of data were used. So now the right graph depicts the training error and validation error as functions of model complexity. So now same thing here, same thing there. And we've got high bias here, high variance here, validation error, training error. The training error, purple line, decreases as the complexity increases. This represents the error it was trained on. The validation error, so this is the purple line. So, and then it increases it. So the purple line decreases. Oh, you know what? There's a bit of a problem here, but anyways, I don't think it's yeah. So moving on, I pointed out earlier that the issue is not about the absolute complexity, but the relative complexity between the data and the model. Let me elaborate on what this means. We think the high validation error happens because our model is too complex and overfitting. It performs poorly when presented with new data from our reality or use case. However, what if what is happening is that the new data is different from the training data? What if the problem is that the training data offered to the model does not contain all the complexity of the reality itself, but of itself it is representing? The problem would not be on the excessive complexity of the model, but on the excessive simplicity of the training data, which is not representative of the reality we are trying to model. While the model is important in any machine learning project, the data is king. We need to pay even more attention to the quality of the data and ensure that the data we are feeding our model represents reality adequately. If we fail to do that, new patterns may exist when we run the model with real live data. New characteristics in the data that the model has not yet seen may exist, which the model has not learned about. Hence, the results will be equivalent to the overfitting phenomena, but in this case, not because the model is complex by itself, but because the data was too simple to capture the complexity of the reality. I know this may sound not easy, and it will sound even more when you realize that data is never static because reality is not static either. You may train a model with a data set representative of the reality at that time, and the conditions may evolve. The model you were using starts to perform badly because data drifted, or more precisely, the reality drifted. This is why every machine learning model and its associated production deployment has a continuous life cycle. The model's validity needs to be constantly evaluated against the evolved reality and retrained when required. If the cause of our overfitting is genuinely the model itself, we need to find alternative, simpler models or algorithms. Some techniques allow us to simplify a model effectively. These are called regularization techniques. We will see some examples later in the following sections. These techniques try to reduce the model's power during the training process to prevent overfitting, I guess I would say, making it more difficult for the model to train. Like forcing I see, okay, that makes sense. Like forcing a tennis player to train with one hand tied in the back, okay. This will have two effects: preventing the model from learning noise and spurious patterns very quickly, and forcing it to focus on the more repetitive patterns. On the other hand, since we let the model run at its full strength once trained, we make it more resilient to data issues because we have forced it to learn more ways to extract the key patterns. Regularization is, in my opinion, one of the most surprising tools and has excellent results. On the other hand, if the reason for our overfitting is the lack of complexity and diversity in the data, then we need to solve the situation in the data, either finding more data or finding more diverse data. We must ensure that the data we present to the model in training represents reality and does not miss critical patterns or contain hidden biases that may mislead the model. One excellent example of this problem is the use case below. So we can see we've got some images here of animals. We're going to predict what kind of animal it is, and then we're going to see what the true prediction here was. So this one we're predicting it's a wolf, and it is a wolf. This one we're predicting it's a husky, which is a type of a dog, and not a wolf, and that is correct. So these, the rest of these are correct here, except for this one. It got incorrect. It predicted it was a wolf, but it's in fact a husky. And we've got an arrow here pointing at this one, so this is the one that is incorrect. Okay, so now I think we've got accreditation for this. Machine learning? So this is a DOI string. Let me pause it and be right back. All right, I'm back. So all I needed to do was put the DOI in Google, and I got this free site, ResearchGate, which offered the paper for free. So that's all I did, and now I have the full paper here, which is important to be able to get the full paper. I'm not going to read the full paper. I'm focusing on this book for now. So there we go. I got that full paper. If I want to look that over later, I have the ability to do so. The model was trained to determine if the animal in the image corresponds to a husky dog or a wolf. After the model training, it would frequently predict accurately, but in some cases, it would wrongly predict a husky as a wolf. After carefully analyzing the images where the model would fail to recognize the husky, they realized most of the images of a wolf used to train the model had snow in the background. So let's bookmark this. So what the model truly learned was the association of wolf with large portions of white in the background, not the physiognomy. And I'll get a pronunciation of this, if I may. So in order to do that, I need to click it twice. Actually, no, I need to highlight it. Here we go. Copy. We'll get a pronunciation of this word. And a definition. So it's a facial. So not as a result of the actual image of the wolf. It's a result of extra factors.
Physiognomy.
So the physiognomy of the picture of the wolf, it might look more like a husky than a wolf. We can see the wolves are different. They're less gray. They're more menacing in their eyes. They're not as kind of calm in their eyes. But we can see each of these images. We have snow in the background for the wolf. But for the husky, we have kind of a more domestic background, just in a field, or looks like maybe at someone's house or something, like a concrete slab. But here we have that same background, so it made an incorrect prediction because it's predicting based on the background and the physiognomy. Physiognomy and the physiognomy of the actual image of the wolf as well. All right, so what the model truly learned was the association of the wolf with large portions of white in the background, not the physiognomy. Not the physiognomy of the wolf itself versus the husky. There was a bias in our data, excessive frequency of white background in wolf pictures, or said differently, lack of diversity. Not enough pictures of a wolf without snow, or not enough pictures of a husky with snow. Either way, the data presented was not diverse or complex enough, and the model ended up learning what it was not supposed to. When we think of a network or cloud use case, we must consider this to ensure that the data we are collecting is sufficiently representative of the reality we are trying to capture and model. I think of this as a bit of an art where we have to play with 3 dimensions: the model complexity, the volume of data available, the problem complexity or reality complexity. So here's a graph for that. As the complexity of the model increases, and as the data, more data becomes available, if the model is not complex and there's not much data, you're likely going to underfit. If the model is too complex and there's not much data, you're likely going to overfit. But if you have a lot of data and you have a fair bit of complexity of the model, but not too much, that's where you get the best fits. And we can see P1, P2, P3. I think these are the problems. So a lot of these problems are improved or solved by having a more complex model with more data available, but not too much. Otherwise, there's overfitting, especially if the data available is low. So for and let's hear what ChatGPT has to say. ChatGPT is awfully quiet today, so it doesn't have to say anything, and it's taking a long time for it to.
This image presents a conceptual visualization titled "The Art of Modeling," illustrating different zones of model performance as they relate to the complexity of the model and the amount of data available. Here's a breakdown. Axes. The x-axis represents the complexity of the model, increasing from left to right. The y-axis represents the amount of data available, increasing from bottom to top. Zones. Likely underfit. This zone is located where both model complexity and data availability are low. In this region, models are too simplistic to capture the underlying patterns in the data effectively. Likely overfit. Found where model complexity is high but data availability is low. Here, models are likely too complex relative to the amount of data, leading to overfitting where the model captures noise as if it were a signal. Likely fit. This zone is where there is a balance between model complexity and data availability, suggesting an optimal fit where the model is complex enough to capture the underlying patterns without overfitting. Problem complexity, P1, P2, P3. These lines represent different levels of inherent problem complexity, with P3 being the most complex and P1 the least. As the problem complexity increases, achieving a likely fit requires either more data, a more complex model, or both.
Okay.
This diagram underscores the importance of balancing model complexity and data availability, tailored to the specific complexity of the problem at hand, to achieve the most effective model performance.
All right, I'm pretty happy with that. So moving on, for a given problem / reality complexity, which we can see with the P1, P2, P3, there will be a curve like the one in the picture. Below the curve on the left, a model will most likely underfit because the model is too simple and the data available is insufficient for a given problem's complexity. Below the curve on the right, the model will likely overfit. The data available is too low and the complexity of the problem is high. Above the curve is the region where the model will likely fit. As the complexity of the problem increases, the curve shifts upwards, requiring more data and more diverse data, and a higher minimum level of model complexity to enter into the fit zone. Key takeaway: a model that is overfitting is not learning, it is memorizing. Okay, so now it's on to regression techniques, which is going to be kind of a lot. It's another mathematical part. So I wish I could use the last 6 or so minutes I have here, but I'm afraid I'm just going to get too far into the weeds and then have to go back and review it. So I think doing it all in one go when I have more time is a much better decision. So yep, that's going to be it for this video. Thanks for watching, and see you in the next one.